All right, today we're going to talk about one of the most important and maybe one of the most overlooked protocols in your network. It's the spanning tree protocol, and it's basically the unsung hero that keeps your network from destroying itself. So let me start with a kind of strange question. In networking, we love to build in safety nets, extra links, backup paths. But what if that very safety net was actually the thing that could bring your entire network crashing down? You see, we build networks with extra connections on purpose. It's called redundancy. Think of it like your GPS giving you multiple ways to get home. If one road is closed, no big deal, you've got a backup route. It creates fault tolerance, which is absolutely key for keeping a network reliable and online. But here's where it gets tricky. Down at layer 2, where our switches live, there's no built-in GPS. Without something to manage traffic, a single piece of data can get caught in an endless circle between switches. And that one frame starts multiplying over and over, creating a digital hurricane that can totally overwhelm your network in just a few seconds. So what really happens when one of these layer 2 loops gets going? Well, the results are not pretty. It's fast and it is catastrophic. The main problem is something called a broadcast storm. You see, when a switch gets a broadcast frame, its job is to send it out of every single one of its ports. Now, in a loop, another switch gets it and does the exact same thing, sending it right back to the first switch. And it just keeps going again and again and again until your entire network bandwidth is choked out. And this meltdown is really a triple threat. First, that broadcast storm we just talked about basically shuts the network down. Second, the switches get totally confused. Their MAC address tables become unstable because they keep seeing the same device on different ports. And third, all your poor devices get hit with multiple copies of the same exact frames, which just creates errors everywhere. Okay, so how do we get all the awesome benefits of having those extra backup links without the terrifying danger of these loops? Well, what we need is an intelligent traffic cop. And that brings us to the Spanning Tree Protocol, or STP. It's this brilliant protocol that lets us have all the physical backup cables we want, but it creates a logical map of the network that has absolutely no loops. It gives us the best of both worlds, all the reliability with none of the chaos. So how does it work? Well, STP makes the switches constantly talk to each other. They send these special little messages back and forth called Bridge Protocol Dated Units, or BPDUs. You can think of BPDUs as little status updates. They carry info like a switch's ID and how much it costs to send data down a path. Then, the spanning tree algorithm uses all this info to draw a map, find any redundant links, and then logically block them before a loop can ever form. Now, the very first thing STP has to do to build this loop-free map is to get everyone on the same page. It needs a single point of reference. And to do that, it holds an election to choose a leader called the root bridge. And just a quick aside, bridge is just an old term for a switch. They're the same thing for our purposes here. The switch that wins the selection becomes the root bridge. It's basically the "you are here" star on the network map. It's the central point, the root of the tree, and every other switch in the network then calculates its single best and fastest path to get back to that root bridge. And the election itself is actually pretty simple. All the switches send out those BPDUs we talked about, and inside is their bridge ID. The switch that's advertising the lowest bridge priority value, well, that's the winner. It becomes the root. And if there's a tie, simple. The switch with the lowest MAC address wins. By default, all Cisco switches ship with a priority of 32,668. So what does that mean? It means, out of the box, pretty much every election is going to come down to that MAC address tiebreaker. And here's a fun fact for you. Since MAC addresses are often assigned chronologically, this sometimes means the oldest switch on your network ends up winning the election. Of course, any good network admin will manually set a lower priority on a powerful central switch to make sure the right one gets elected. So, once the root bridge is elected, STP starts the real work of building that loop-free topology. And this is where you can really see how smart the algorithm is. To figure out the best path back to the root, STP uses a metric it calls cost. It's actually really simple. The cost is based on the speed of the link. The faster the link, the lower the cost. So, a really fast 10 gig link has a tiny cost of 2, while an old, slow 10 megabit link has a huge cost of 100. STP will always pick the path with the lowest total cost. Think of it like golf. Lowest score wins. Next up,
STP assigns a specific job or a role to every single port on every switch. Each switch that isn't the root looks at all its connections and finds the one single fastest path back to the root bridge. That port becomes its root port. Then, for every cable segment that connects two switches, the port that's closer to the root becomes the designated port, and its job is to forward traffic for that whole segment.
So here's the magic. By making sure there's only one root port per switch and only one designated port per segment, STP guarantees there is only one active path between any 2 points. So what happens to all the other ports? Well, they get put into a blocking state. They're not dead. They're physically connected and ready to jump into action if a main link fails. But they don't forward any data. And just like that, no more loops. It's pretty elegant.
Now, the original spanning tree protocol was an absolute game changer for making networks stable. But it had one big flaw. The time it took to recover from a change, what we call convergence time, was incredibly slow.
Back in the day, when a link failed, a port running classic STP had to go through a whole process. It included a mandatory 15 seconds of just listening, and then another 15 seconds of learning. All told, it could take up to 50 seconds for a backup port to become fully active. I mean, can you imagine waiting almost a minute for your connection to come back today? In the age of Zoom calls and constant streaming, that's just not going to fly.
Thankfully, things have gotten a lot better. Modern versions like Rapid per VLAN Spanning Tree Plus or just Rapid PVST Plus have totally slashed that recovery time. We're talking less than 10 seconds, and often it's much, much faster. That rapid recovery is absolutely essential for the kinds of networks we rely on today. And you can really see the evolution here. The original STP was slow. Then came the industry standard, RSTP, or Rapid Spanning Tree, which was a huge leap forward. Cisco's proprietary Rapid PVST Plus is just as fast, but it adds a twist. It runs a separate spanning tree map for every single VLAN. This is super flexible, but it also means the switch's CPU and memory have to work a lot harder to keep track of it all.
So how did they get it so much faster? Well, they made some really clever changes. They simplified the port states, for one, but the real game changer was adding a new role called the alternate port. This port acts as a hot standby for the root port. If that main path goes down, the alternate port can take over almost instantly, without having to wait through all those long timers. It makes the whole network way more resilient. You know, the journey of STP from a 50-second recovery time down to just a few seconds really tells a bigger story about networking. Our demand for speed and for 100% uptime just keeps going up. And as our digital world gets more and more complex, the constant evolution of these foundational protocols, like Spanning Tree, is what keeps everything connected.